While systems exist for capturing geometry, color, and normals of objects, they are cumbersome and time-consuming for non-experts to employ on a large scale. We present a system with which archaeologists and conservators can efficiently acquire thousands of fresco fragments. We have deployed our system at the Akrotiri excavations on the Greek island of Santorini, also known as Thera. The main challenge with acquiring thousands of fragments is limiting the manual labor required to capture and process each fragment. Our acquisition setup consists of a flatbed scanner to capture images and normals, and multiple 3D scanners to capture geometry. The operator places the fragment face down on the scanner bed and clicks a single button to acquire the scan. Our scanning software automatically detects the fragment in a pre-scan and performs the final scan with no additional user input. The process is repeated for 4 orientations each of the front and back faces to provide multiple lighting directions for normal reconstruction. For 3D scanning, the operator places the fragment on a calibration sheet to determine the necessary start and end laser positions. He or she then places the fragment face down on a turntable, enters the laser parameters and fragment ID, and clicks the scan button. When the scans are complete, the operator turns the fragment over and scans the front. To align all scans from a single sequence, we introduce the multi-way ICP algorithm. Traditional ICP alignments fail here because the flat front surface does not converge to a stable local minimum. Instead, we note that each scan is rotated the same amount with respect to the previous scan. Multi-way ICP takes advantage of this to find a single rotation which simultaneously aligns all scans to each other. Next, we must align the front and back surfaces to each other. When the fragment is upside down, the front surface is lying flat on the turntable. We therefore extract the front surface's plane in the front scans and rotate these to coincide with the turntable's plane. In this way, we reduce the problem of aligning the front and back surfaces to a 2-dimensional alignment problem, which we solve with a rough initial estimate and ICP. To align 2D images to the 3D geometry, we use an image alignment algorithm which maximizes normalized cross-correlation. Although our alignment algorithms work in the vast majority of cases, there are occasional failures, so the operator verifies the results and corrects any errors. To be practical, this must take only seconds per fragment. The operator first checks the final merged 3D model. If it is correct, he or she moves on to the next fragment. If the front surface is misidentified, the operator clicks on it and the correct alignment is computed. If the front and back surfaces are incorrectly aligned to each other, the operator positions the front surface approximately, and ICP refines the estimate. Because the alignment of front and back surfaces is constrained to a plane, the manipulation is both quick and intuitive. To verify registration of the 2D images to a fragment model, the operator flips between the 2 images. If there is a misalignment, the operator interactively provides a very rough alignment, which we refine using the minimization described in our paper. We were able to verify and correct 150 fragments in 10 minutes. We present a new 3D matching algorithm which is appropriate for matching the many fragments which have no surface decoration at all. First, we generate a regular sampling of each fragment edge, which we call a ribbon. Then, we can select a portion of one fragment's ribbon and compute its alignment to another ribbon without searching for point correspondences. We incrementally shift the overlap region by one sample and compute the new alignment in constant time. In summary, our system allows users to capture 2D scans, normal maps, and 3D models for tens of fragments per hour. In addition, we are able to efficiently suggest matches between fragments that take, on average, several weeks to find without computer assistance. We believe that by addressing the scalability and usability challenges of acquisition and matching algorithms, our system will make these technologies practical in an archaeological setting.